Hi everybody. I am Simone Bronzini, CTO of Chainside. Brief presentation. Chainside is a startup that allows merchants to accept bitcoins in an easy way. We started off with a e-commerce system, and now we are developing a POS application, which are merchant applications that allow merchants to accept bitcoins in face-to-face payments. But as a company, we also contributed to open source development. In particular, we published a couple of Bitcoin libraries that are used to like manipulate and create complex Bitcoin transactions. One is in Python, it's called BTC-Py, and the other one is in JavaScript, and it's called BTC Node.js, as you can see. I'm also part of an association of academics that's interested in blockchain-related topics, which is called BEN. This is the Italian branch, and it's actually a worldwide association, and we represent the Italian branch, and you can see some numbers about the association, and if you're an academic and want to join, just go to the website and you will find all the needed instructions. Okay, so I'd start off by what is consensus. Like the idea of consensus is I have a distributed network of nodes, and I want them to agree on a common state. I want them to agree on a current state of transactions that happen inside this distributed system. So, historical attempts at solving consensus were what we now call permissioned, which means this network of nodes is actually a network of nodes I know, like in a database. I have my database system, I have some nodes, I know which ones they are, I can decide who has writing permission, who has reading permission, and so on and so forth. Now, traditionally, the systems are based on majority on these nodes, because I have a fixed number, and so I can say like what's exactly a majority. I have a clear definition of majority. Actually, with Bitcoin, like the first permissionless consensus protocol was Bitcoin, and the main idea is that I don't know how many nodes are going to be in a network, because nodes can come and go. You can just download a piece of software and you join the network. So, in this case, I don't have two important things. One is a concept of majority, and also I don't have the ability to decide who has writing permission or reading permission. Well, actually, I can't say it from the beginning who has writing permission, so I need writing permission to be decided on the run, like while the system is working. So, in the case of Bitcoin and other blockchain system, we usually pay writing permission by consuming some scarce resource. In the case of Bitcoin, that's electricity. And usually, reading permission is for everyone. I just plug a node and read the blockchain. This mechanism is known as proof of work, and some other attempts have been made and of trying some other resource to consume to get writing permission. Well, let's see what are the pros and cons of these systems. Well, mainly, as I told you, like the most common approach, the old approach to this problem, had the fact that we needed to know how many nodes were there, and I could coordinate them in some way. In the other case, like in the permissionless case, since I don't know how many nodes are there, I need this way of consuming a scarce resource, because everyone can deploy a lot of nodes on the network. And then in this case, if I used a majority approach, everyone could subvert the network by deploying a lot of nodes. So, but this permissionless system is fantastic, but it has a slight problem. When I want to upgrade a protocol on a permissioned network, well, I can just shut down all nodes, I control them, and then I upgrade the software and I rerun the network. In the case of Bitcoin and permissionless systems in general, well, how do I upgrade the network? I can't just shut down all nodes. So I would like to show you how this is achieved by giving you some examples on how this was done throughout history. So one of the first important Bitcoin upgrades happened like this. So the creator of Bitcoin just posted on a Bitcoin forum, please shut down all nodes, upgrade the system, and rerun them. And of course, you could do this when you had like some tens or hundreds of nodes, and everyone who was involved in deploying these nodes was also involved in development and was following forums and so on and so forth. But now in the Bitcoin networks, there are thousands of nodes. We are around 10,000 of nodes, and we're not even sure how many are there actually. So I can't just upgrade the protocol like this. Okay, now what's the problem of upgrading a protocol like this? Imagine that we have two sets of nodes that are following different consensus rules. Like yellow nodes are following old rules, and blue nodes are following new rules that are the consequence of an upgrade. Well, as you may know, in Bitcoin, for example, we have blocks that gather transactions. So transactions are organized in blocks, and we have a chain of blocks that every node follows to know which transactions are confirmed. So in this case, let's say that the yellow transactions are the ones that are produced by old nodes, and the blue transactions are the ones that are produced by new nodes. What happens is that we were just producing yellow transaction, and at some point, a new node produces a block with a new kind of transactions that the other ones don't understand. So in this case, the yellow nodes are going to reject that blue block because it's invalid for them. It follows different rules. And so they're going to keep mining on the previous block they knew, and so on and so forth. So in a case like this, the network is going to split. This split means exactly that there is no consensus between yellow and blue nodes, so there is no fixed state that they agree upon. And pretty much in cryptocurrencies, at least, this means that we have created two cryptocurrencies from one, and this is no good news. So how do we avoid a situation like this? Well, we have a set of rules that all nodes follow. It's the yellow set you can see there. And we can do an upgrade that changes these rules in many different ways. So one way would be having a new set of rules, that's the first one there, which has an intersection with the old rules, but has some new rules that the old nodes don't understand. Another way would be having a whole new set of rules, so nobody understands each other after the upgrades. But the most common and most interesting cases are the last two. So in the first one, the new rules are actually a subset of the old rules. And in the fourth case, the new rules are a superset of the old rules. Well, let's see what happens in these cases. Okay, in the case where I just produce new rules that are completely incompatible with the old ones, the network is going to split since the moment of the upgrade. That line that you see is the moment where the new nodes upgrade, and well, the two sets of nodes are going to produce completely different blocks that are not understood by the other set. And this is an unavoidable split. In this case, the blockchain is not going to split as long as there is a block that's inside the intersection of the rules. But as soon as a block that's not understood by the other party is produced, then the network is going to split, and this is unrecoverable as well. Well, this is a very common case, and the most used actually to upgrade Bitcoin. Well, I do a new set of rules that is actually a subset of the old rules. This means that the new rules are actually compatible with both sets of nodes. And the point there is that two scenarios can happen. The top scenario is the one where new nodes start producing blocks in a subset, and if they have a majority of computational power, are faster in producing blocks than the other set of nodes. And so the new rules is followed by the majority of the network, and the longest chain is the new one. And this means that, of course, those new blocks are compatible also with old nodes, so it's backwards compatible. And so the old nodes are going to accept also the new chain. Instead, in the case where, the second case, the bottom case, when the old nodes are faster in producing blocks than the new ones, then for the new nodes, the old blocks are not valid because that's not in the intersection of the rules. And so the network is going to split at least as long as the yellow chain is longer. But at some point, if enough nodes upgrade, then the chain will converge. Sorry, and this is called soft fork commonly in cryptocurrencies. Well, the final example is that of a so-called hard fork. That means that the new rules are a superset of the old rules. And that means that as soon as a new block is produced, that's not compatible with the other nodes. The problem with this kind of split is that as long as there is at least one node that's following the old rules, and that's mining blocks, the split is not going to recover. So in the first case, like in this case, we had actually a situation where at some point we could converge as soon as the majority of nodes was adopting the new rules, while in this case, as long as there is even one node that's not following the new rules, the chain is going to be split. So let's see an example. There has been a long debate in Bitcoin about block size. So in Bitcoin, blocks are capped to 1 megabyte. You can't produce blocks that are greater than that, and because like the nodes would reject them. Of course, there has been like a long debate about this because of transaction throughput in Bitcoin. So they wanted to increase the block size to accommodate more transactions and so on. But there are many problems about this. But one of the worst problems is that most solutions that were produced to achieve this were hard fork. So what would have happened is that we were producing regular blocks, then at some point someone produces a huge block, the old nodes don't understand that and keep mining on the yellow ones, and then the network is split forever. So what's an example of a soft fork? This is, we have some examples of this, and it was used a lot of times to upgrade Bitcoin, actually. So we need to go a bit in depth about how we sign transactions in Bitcoins. So I don't know if you know this, but Bitcoin uses ECDSA. It's elliptic curves cryptography. And Bitcoin's transactions are identified by the hash of the transaction. So I have a transaction, I serialize it, I compute the hash of the transaction, and that's how I identify a transaction. The hash is the identifier. Well, the problem is that signatures in Bitcoin can be malleated. This means that these signatures can be changed after the transaction was produced. So this is an elliptic curve, and that's the one used by Bitcoin. Well, actually, that's a representation on the real numbers. It's a bit different because it's on ZP field, but it wouldn't be seeable in that case. So let's imagine it on the real numbers. And a signature of a Bitcoin transaction is actually a point on that curve. So let's see what can go wrong. Well, I produced a signature that's a point there, but anyone can produce a valid signature for the same transaction, of course, just by inverting the point on the curve. I just see a signature on the network, I change it to the other point on the curve, and rebroadcast the transaction. So, of course, like the semantics of the signature are the same, so this is not actually an attack on who's signing, usually, because the signature is valid, and I have signed, like the one who malleated the transaction is signing the same thing. But this leads to a problem, and the problem is that the hash of the transaction changes. So I was identifying two equal transactions by two different IDs. That's mainly the problem. So they fixed this by saying we will stop accepting signatures that are on the higher end of the curve. So if I see a signature that's like the second one there, that's a good signature. If I see the first one, I reject the transaction. Of course, this is a kind of consensus rule change that is a subset of the old rules. So I'm accepting less transactions. So in this case, it's still in the case of a soft fork, and as soon as the majority of nodes accepts this rule, the network will not split, because the new nodes are going to reject some transactions, but the ones that are included in the block are compatible with the old nodes that were accepting both kinds of transactions. Okay, so what we gather from this is that we can do upgrades, but we can do them just as long as we have minus coordination. So who's producing block must coordinate so that the upgrade, like the majority of miners accept the upgrade before locking it. So in Bitcoin, this is achieved by miners signaling for readiness for an upgrade. So as soon as a huge majority of miners signals that they are ready for an upgrade, then all the nodes in the network can see that they are ready to enable it, and so the upgrade is locked in and it's deployed. Okay, so I would like to focus a bit more on this transaction malleability issue, because this is going to lead to another upgrade that was done a year ago, last August, and it was a very important Bitcoin upgrade because it allowed Bitcoin to scale without increasing the block size. I mean, it also increased the block size, but that was a side effect. Okay, so why was this malleability a problem? There were like two main problems about this. One was actually a problem that could be solved just by having a bit of attention on your code. So what happened? Since I could have two transactions that were identified by different identifiers, so what happened was that, for instance, I had a wallet. I don't know if you remember MTGOX or if you heard about that. It didn't end well. But one of the problems they had was, well, when the user was withdrawing money from the wallet sent a transaction, let's call it A. But of course, anyone could malleate this transaction and change its ID. So I could produce A prime that entered the blockchain instead of A. Then I went to the wallet and said, okay, the transaction you sent me never entered in the blockchain, so please send me another one. Of course, this could have been avoided if MTGOX had a good system of monitoring the blockchain and checking which transactions were equal, but they didn't. So they resent the transaction, and so on and so forth. You could do this many times. It was funny. And for these problems and many other problems that they had on their code, at some point, MTGOX just lost a lot of funds and closed, and there is a process right now to give back some funds, or at least the ones that were covered, to the users. But of course, this is a malleability problem that could be solved with good accounting. You could just do good accounting, and you could avoid this. But there is another problem that you can't go around, so this malleability issue needs to be fixed once and for all. Okay, let's see how this malleability is a problem, mainly for the scope of scaling Bitcoin. So I'll just do a brief introduction on a scaling solution for Bitcoin, and we will see why malleability is a problem for this solution. Okay, since we just said that increasing the block size would have been a problem for many reasons, we need to find a new way to accommodate more transactions in a Bitcoin network. So the idea that was found was this one, was creating so-called payment channels. This meant I have a transaction on the blockchain, I start producing transactions that never hit the blockchain but move money outside the blockchain, and then at some point I can produce like a pretty much unlimited number of transactions outside the blockchain, and then I can just converge again on the blockchain and write there the final balance. This is a very good solution because it removes weight from the blockchain, but I can still do transactions with the same guarantees. So why is malleability a problem here? The problem is that in Bitcoin, transactions have this structure. So every transaction actually refers a previous transaction. So what I'm spending is not actually Bitcoins, it's previous transactions I received. So in that case, you can see that transaction J is spending two outputs from transaction K. This means at some point I received transaction K. It had 5 Bitcoins for me. I want to move 4 of those Bitcoins. And so I produce transaction J that uses 1 Bitcoin from the first output, 3 Bitcoins from the third output, and then moves them to someone else. So we have a chain of transactions, and all these transactions are like referred to the previous one by their ID, which is the part that can be malleated. So, well, what happens if I change, in a bottom case, what happens if I change the signature of transaction J? Well, the ID of transaction J changes and becomes H. So if I had produced a new transaction that was pending from transaction J, the reference to the previous transaction was destroyed. And so I, just changing the signature, I could invalidate the next transaction. Of course, all this could happen only if these transactions were not on the blockchain, because as soon as they're on the blockchain, they are just written there, you can no longer change them. So what happens in our payment channel case? That script sig, that red box you see there, it's what contains a signature. So I have a transaction A on the blockchain, I produce a new transaction B off-chain, and I want to start a payment channel with that. So I produce a new transaction that spends from B, And I could do this for many and many times. But so what happens if someone changes the signature of B, which is not on the blockchain, so I can pretty much change it? Well, it happens that maybe on the blockchain goes transaction B prime, which is exactly equal to transaction B, except the ID has changed. So the reference that C had towards B is no longer valid. This invalidates both B and C, because B prime is the same transaction as B, so it entered the blockchain, but C is referring to a transaction that no longer exists. So the problem with malleability here is that we can't do payment channels if we have transaction malleability. So there was an upgrade called SegWit. Maybe many of you heard about this. It was quite important. There's been a lot of work. They worked for 2 years to deploy this. And the main problem is that they needed to change the way transactions were identified on the network, but they needed to do that in a backwards compatible way, which is not easy at all. Like, the solution is very simple. I just need the way I compute the ID of the transaction. But how do I do that in a backwards compatible way? That's more complex. So, but let's see what's the idea of SegWit and how it impacts on this payment channel thing. Okay, what was first called a script sig is now called a witness. It's still the same thing, but it's a new data structure that's appended to transactions. That's still the part of the transaction that contains signatures, but that doesn't take part in the computing of the hash of the transaction. So what happens in our payment channel case, I had these two transactions, C spent B. If someone modifies B's signature, that's going to be a new witness, but the ID is still B. So B is no longer valid, but the reference to B is still the same. And so C is still a valid transaction. I didn't break the whole payment channel. I just put one of the transactions in the payment channel on the blockchain, but the other ones were still valid. So, of course, this is a very delicate upgrade, because I'm changing the way I represent transactions. So how could they do that in a backwards compatible way? Well, transactions in Bitcoin could be represented like this, even though it's not very accurate. So in this case, what we mean by this is that in the output of a transaction, we represent it as a lock, the spending condition of the transaction, and we represent it as a key, the signature that matches the spending condition. So what I'm actually saying when I say from Alice to Bob, what I'm actually saying is that someone who has the private key that matches the public key by which I identify Bob can spend this transaction. So when I do from Alice to Bob, Bob needs to sign the transaction to spend those money. So, and so on and so forth, like the next transaction is the same. So I have some spending conditions, and I have the data that satisfy those conditions in a signature, in a script sig. So how can I do this? Like, how can I remove exactly the part that the nodes are signing? Like, if I do this, then that means that the nodes cannot validate signatures. And that's exactly what was done. So in SegWit, transactions change to that structure there. And this means that the signatures are actually outside of the body of the transaction. Well, this is not very accurate. It's not exactly outside of the body. It's actually in a part of the transaction that doesn't take part in an ID computation, in a hashing computation. So, but of course, the old nodes don't even know what a witness is because they didn't upgrade that software. And so how can they validate those transactions? Well, they don't. What they managed to do is that they started producing transactions that old nodes thought that could be spendable by everyone. And this means that we represented that as open locks. So an old node is going to see transactions that are spendable by anyone. And when I spend those transactions, the old node is not able to validate the signature because it doesn't know the witness structure. But of course, since that transaction can be spent by anyone, the old node doesn't even need to validate the signature. And so the problem with this is, of course, old nodes cannot validate transactions properly. But as long as a majority of miners can do that, only valid transactions are going to enter the block. So we also gained the ability through SegWit to slightly increase the block size. And the idea is that if at first we had the whole transaction inside the block, now we have these additional data structures where the signatures are. And since it's a separate thing, I can compute the size of that part in a different way. So we also managed to increase the block size in a backwards compatible way, which was longly debated. So all in all, well, what we've seen is that, like in consensus systems, like upgrading them is very difficult. And also, like very simple solutions, like changing how you compute a hash of a transaction, can be must be deployed in a very careful way and in a very complex way. And well, just as an addition, as Chainside, we are also following thesis in accordance with Sapienza University and UZH. There are some topics. If you're interested, you can just contact me and we can discuss them. If you need to have a thesis and you're interested in the blockchain, in blockchain-related topics. Also, as I told you, Blockchain Education Network, you can join it. It's very nice. Thank you.